I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists.
Tonight's Wonderfest speaker is Tucker Hiatt, founding director of Wonderfest. I gotta give at least a fairly serious introduction. I'm not supposing that I would hand this microphone to Tucker in just a minute. Tucker earned bachelor's and master's degrees in physics from the University of California, go Bears, and go Slugs, with the idea of becoming a physics teacher. I have to read my own bio, this is embarrassing. Indeed, Tucker taught physics at UC Santa Cruz, Punahou School, University High School, and Branson School here in Berlin, ultimately earning the Amgen Award for Science Teaching Excellence. En route to creating Wonderfest in 1997, Tucker worked at the Exploratorium, where he built an exhibit. He worked at the Berkeley SETI Research Center, where Dan Wertheimer comes from, where he helped write SETI at home software. And he did not work at Stanford University, where nonetheless, he somehow became a visiting scholar in the Stanford Chemistry Department. That remains a deep mystery. You think the Fermi paradox is tough. Please welcome Wonderfest go-to fill-in speaker, Tucker Hiatt. All right, let's see. We got a good cartoon here. We got some formal title here. And we've got a good question. Why are we here? I am a philosophical sort, so you can go that deep if you want, but I mean just here to understand this subject. Why do you and I care about understanding E equals mc squared? Here's a cartoon that I think helps explain it. It comes from Sidney Harris. It shows humanity's achievement, and it is perhaps up there near the top of our grasp of reality, that it could entail this equation. That's really quite an accomplishment. I imagine you want to share in that understanding, in that grasp, in that climb. After tonight, I will go down and be the little man here in the watching TV. Maybe that'll be some Olympic reruns. But for now, I, with you, am going up there. Okay, here's another reason for this understanding this topic. It does seem to have rather practical and perhaps ominous implications. Here's the cover of Time magazine soon after the detonation of the first two fission bombs in 1945. And it shows the equation inscribed there in the mushroom cloud, and Albert's face there is at least showing concern. This is a serious subject. He said, Einstein said, if only I had known, I should have become a watchmaker. Now it's interesting that I've studied this quite a bit. It doesn't seem like Einstein's work directly, certainly not directly, contributed to the creation of the bomb. He didn't work on the Manhattan Project, except perhaps indirectly. But I'm almost afraid that in his quotation, he meant, if I had known, I should have become a watchmaker rather than a physicist. And that hurts. I don't know if that's true. Maybe at the end we'll revisit this question. All right. So I'm going to make a little, perhaps a tactical error here. I'm going to reveal the punchline, the takeaway idea from this talk. So on the next slide, it can be expressed in 3 words. Energy has inertia. All right, so you can go now if you want, that's it. But it does take some explaining, and I hope that explaining, that deeper understanding is truly fun for you. All right, so let's start with the equation itself. We're going to proceed through the terms in unusual order. We're going to go from right to left. That'll please our Arabic and Hebrew-speaking friends. All right, so we'll start with the speed of light, little c. All right, but first, we got to go back. I warned you, I'm a physics teacher. What is speed? It seems like a fairly easy idea, but let's just make sure. Okay, speed is defined as distance divided by time. If you travel 1 meter, you far, in 1 second, that's about the duration of 1 human heartbeat, if you're not too excited. If you travel 1 meter in 1 second, you divide those two numbers, you get your speed. 1 meter per second. Sure. Now we're more accustomed to miles per hour, but I'm going to ask you to adopt the SI, the International System of Units for tonight. It'll make things easier, trust me. Along with this definition of speed, I'd like to consider that word in capital letters there, dimensions. Physicists have found that it really helps to look at the universe in terms of fundamental physical dimensions. I don't mean strictly the spatial dimensions. We'd say length, width, and height. I'm talking about the physical dimensions, one of which is length. But length, or sometimes called distance, is the same kind of thing whether you measure it horizontally, vertically, deep into the ocean, forward and backward. Those are all measurements of a length. So length is regarded as a fundamental physical dimension. When you write the word as a dimension, you often capitalize it. That's why I've written the word dimensions there in capitals. All right, so I've talked about these deep fundamental dimensions. Distance is one, time is another. Nobody has figured out how to turn time into distance completely. You can't, at least easily, measure time in meters, but you can measure it in seconds. So we'll stick with meters for distance and time for seconds in this talk. All right, so let's entertain this question right now. How fast are you moving at this moment? Now I'd ask you to humor me. If you're sure you know the answer, first of all, try to give your answer in meters per second, but if you must, use miles per hour. But please raise your hand if you have an answer, not if you have another question. No questions yet. This is the question. How fast are you moving right now? Anyone want to take a stab? Again, don't answer with a question. Answer with a number. Doug.
24,000 miles per hour.
Ooh, 24,000 miles per hour. Impressive. If that were true, it seems like you ought to be holding on. Yeah, it just seems weird. Yeah. I think, oh, yes.
What if you're still? We're sitting.
Yeah, how about 0? It sure kind of feels that way.
We're moving around something.
Ah, okay, so Judith, you said 0 at first because here you are sitting still. But you'd argue, as Doug just hinted, we're also moving on the Earth. Or the Earth is turning and we're stuck to the Earth. In fact, if we were at the equator, we'd be moving in a circle the size of the equator itself, and that's about 24,000 miles. Maybe that's where that number 24 came from. 24,000 miles, and we complete that big circle, if we're at the equator, once a day. 24,000 miles in 24 hours. That means our speed, distance divided by time, is 1,000 miles per hour going around with the Earth as it turns. Now we're not at the equator. We're at a higher latitude, so our speed is slower, but it's still mighty fast. It turns out to be closer to 800, instead of 1,000 miles per hour, 800 miles per hour. So hold on. These HopMonk tables are especially valuable right now. No, you know, it's funny. This is what makes speed so strange. You may have guessed, and you kindly resisted answering my question with another question. How fast are you moving right now? Relative to what?
Right.
Yeah, you need to refer it to something, to some reference frame. So just a minute ago, we calculated our speed, if at the equator, as 1,000 miles per hour relative to the center of the Earth. Yeah. But the Earth, yes,
And we're
Linda.
also going around.
The astronomer,
That
Linda,
way.
just said we're also going around the sun,
Right.
right? The Earth is moving once a year in its orbit around the sun, and I've heard it's going something like 18 miles per second, really cruising, much faster than the 800 miles per hour we're experiencing right now. So we're on a turning sphere here. The Earth orbits the sun. The sun, you probably know, orbits the center of the Milky Way galaxy. And that galaxy orbits near the center of mass of a local cluster, and there are superclusters we're a part of, and it seems to be never-ending. So you might say, as I did when I first watched Star Trek, I'm an old school Trekkie. For me, Star Trek is Kirk and Spock and Sulu. And I remember those episodes where Kirk would turn to Sulu, the helmsman, and say, Sulu, what's our speed? And Sulu would say, warp 4, Captain, warp 4. Now, I don't know, it is written somewhere what that means, but how about this? Why didn't Sulu say so rudely to his captain, I think this is why he didn't say it, relative to what, Captain? You know, you'd think, what, the center of the galaxy, maybe? Or could the Enterprise somehow measure its speed through space? Maybe that's what we really want to know. What's our speed through space? The problem is that space is not like water that an ordinary ship goes through, right? Space isn't like air that an airplane flies through. You can measure your speed in a ship relative to the water, or your speed in an airplane relative to the air. But relative to space, space is not a thing. Space is nothing. Space is no thing. It turns out that nobody has solved this problem, and Galileo first figured this out. This is Galilean relativity, not fancy Einsteinian relativity. If the question is how fast are you going, there is no good answer, no relative to space answer. You have to say it's relative to something like an object, perhaps the sun or the center of the galaxy, but there is no absolute meaning to the concept of speed. You've always got to refer it to something. And that idea still blows me away. And it may be Galileo's discovery of that idea may have broken the spell of the ancients, particularly a very smart ancient named Aristotle. It took almost 2,000 years to figure out that speed is relative. And that was the start of Galilean physics and led to Newton and so on. All right, so we don't move through space. So conclusion here is speed is relative. All right, so the best answer to what is your speed is simply a cocky relative to what, sir? By the way, if pulled over by the CHP, yeah, watch out. I don't think they'll buy it. Do you have any idea how fast you were going? Relative to what? All right. If these ideas have intrigued you and you want to share them with somebody, but you didn't memorize what you just heard, there's a video, a TED Ed video titled "How Fast Are You Moving Right Now?" Now, TED videos involve humans talking on stages. This is entirely animated. I think it's 6 minutes long, and it's a TED Ed video. Again, the title will lead you to it. And it's really a beautiful, beautiful video. I say that because I wrote it. I didn't do the narration, but I think it's good. All right, let's see. Now, I'm going to show you a table of constants, physical constants that may send a few chills down the spine if you do have, I hope this isn't the case, but you don't have entirely pleasant memories of high school physics. Maybe you didn't even take it, so the side of such a table as this is not so bothersome. It's just opaque, it's just unintelligible. But despite the fine print here, you see some numbers. Here's the universal gravitational constant. Here's the acceleration due to gravity, 9.8 meters per second. Weird numbers, weird units. But there is one number on this table. There's one number in this table that is by far the strangest. Not in its value, but the fact that it's on a table of supposedly universal physical constants. Universal physical constants. Given what we just learned about the beginnings of relativity, do you see a number up here that just shouldn't be there? Terry, I saw you nod. This one right here. The speed of light, little c, 3.00, and that's a real measurement, 3.00 times 10 to the 8th meters per second. It's a very great speed. It's around the world at the equator about 7 times in a second. Very fast. That's impressive, but that's not what's strange about this number. What's strange is that it's a speed. What is a speed doing on a table of constants when there's no reference frame cited. That is so bizarre. Lots of other bizarre numbers here, but none stranger than that, because there is no reference frame cited. Well, maybe that's relative to empty space. No. What this means, and this is one of the more astounding things anybody has learned, I say, about reality, is that the speed of light is invariant. All right, now I need to make it clear what that means. So let me show you a practical implication of this for any light beam. If I'm going to claim something as strange as this, as I claim it is, I better at least first demonstrate it and then do some explaining. I've got here magician's smoke, fake smoke, non-toxic. Okay? But I'm going to spray it in this direction, avoiding key wonder knots. But I'm going to shine a laser beam through it. Now, right now, when I shine this beam, you can see it as it reflects off the door. But it's rather hard to see the beam moving through the air. So to see the beam, let's give it something to scatter off of or to reflect off of, and that's why I got this smoke. Yeah? Now the beam becomes visible. And you can really imagine something tearing across the room here at 300 million meters per second. And imagine measuring its speed. All right, but I'm claiming that that speed is a number that does not depend on the speed of the laser that I'm moving. It doesn't depend on the speed of the device I might use to measure the speed. It's invariant. Imagine that I made the same claim about not the speed of light, but the speed of a major league pitcher's fastball. Suppose that major leaguer standing on the mound can throw a ball always at 100 miles per hour. And somebody dares to claim that the speed of the ball is invariant. You can't change it. So that would mean if you were dumb enough, as the batter might be, to run or first just the ball hits you, ouch. And now you run towards the ball and let it hit you. It would still hit you at 100 miles per hour? No. Your speed, let's say you could run at 10 miles per hour, would add to the speed of the ball and you'd get hit by a 110 mile per hour fastball. Even more unpleasant. Speeds add. If you're the pitcher, you would like to be able to run and throw the ball. Because if you could run at 10 miles per hour and still throw at 100, your speeds would add, and you now have a 110 mile per hour fastball. You would be the best major league pitcher there is with some accuracy. And that's the way speeds add for everything in the universe except light. By the way, pitchers, I understand, baseball insists that pitchers keep their foot on the rubber as they pitch, and this means that they can't run while throwing the ball, because they certainly would do that to add their speed, or just a little speed, to the speed of the pitch. But not for light. It doesn't work. Yes?
Question, how do scientists know that the speed actually is invariant?
Okay. So what sorts of experiments have been done to measure the speed of light? That's a very good question that has inspired lots of scientists to try to come up with novel ways of measuring the speed of light. Because you're guaranteed a Nobel Prize if you can use a light beam and any sort of measuring device that finds a speed other than 300 million meters per second. Guaranteed. In fact, this is it. Now, notice I'm not answering your question because there are just so many, not that I know them all, but there are just so many possible answers. How do you measure the speed of a beam of light? Here's the, I'm making an extraordinary claim here, right? That good old Carl Sagan said extraordinary claims require extraordinary evidence. And this is a most extraordinary claim, that the speed of light is invariant. There better be a lot of good evidence for this. Yes?
Does the speed of light change when it travels through something like a glass or
Ooh.
water?
Yeah. Does light slow down, perhaps, as it travels through glass or water? It does, but that's because of the absorption and re-emission of the light as it goes from molecule to molecule of water. Say, let's choose water. Between the molecules of water, which is a perfect vacuum, light travels at 300 million meters per second. So it's like a train that always travels at the same speed, except when it stops at the stations. And for a light beam going through water, the stations are the water molecules. Momentary, very brief absorption of the light and then re-emission. And that gives an overall reduction of the average speed of light through glass. But in vacuum, the speed of light is 300 million meters per second. Yes, sir?
Who discovered that the speed of light is invariant? How did they discover it?
Oh, boy.
You did.
I want to say Einstein, but I don't know that. He certainly drew the most wonderful implications from that. But that he was the first to realize the invariance of light, I just don't know.
It was fundamentally a mathematical discovery.
No, well, actually, this could be because the equations that describe the light beam were discovered by a guy named James Maxwell, a Scottish physicist. Maybe this is 1866, somewhere around that. And Maxwell realized that if you could measure what's going on inside a light beam, there was both a changing electric field and a changing magnetic field. That's why we call light electromagnetic radiation. Electric field and magnetic field. And Maxwell discovered from the math of how those fields induce each other, is the fancy way of saying it, in a light beam, is he realized that the ratio of the here's a varying electric field, and at right angles a varying magnetic field. They're inside that laser beam that you just saw here. If I had a magnetic field probe here and an electric field probe, very talented fingers, and I could stick them into the beam and measure those field strength as the beam goes by, Maxwell showed that if he took the ratio of the electric field maximum, because it's varying, divided by the magnetic field maximum, he would get the speed of the wave. He'd get the number 300 million meters per second in metric units. And he gets that number no matter what kind of light it is. It doesn't depend on the frequency or wavelength of the light, the color, let's say. It's true for every light beam. The ratio of the electric field maximum to the magnetic field maximum is always this number, the speed of the wave. Now, that means that Maxwell could have developed the theory of special relativity that Einstein did. But Maxwell was plenty brilliant. He didn't do it. And it didn't happen at least it wasn't brought together in this coherent theory called the special theory of relativity until 1905. So I don't know who first recognized the invariance of the speed of light. But again, if you can show that it's not true, Nobel Prize City. It's no joke. Yes?
Experimentally, wasn't it Michelson and Morley that did an experiment where they went up to a mountain and they shined a light in two different directions?
Yes.
And showed that even though the Earth was moving in a certain direction, the amount of time it took for the light to reach a sensor on another beam was the same.
Yeah. This question involves what is called the Michelson-Morley experiment, which precedes Einstein's paper in 1905 that laid down the foundations of special relativity. And that experiment, the Michelson-Morley experiment, showed that as the Earth moved around the sun, light didn't travel any faster in the direction the Earth was going than at right angles to that direction. And that shocked people. But somehow, I don't think, maybe there were some that were saying light's invariant, I just don't know. But it turns out, I've heard, that Einstein he perhaps didn't even, that's hard to believe, he didn't refer to the Michelson-Morley experiment in the development of special relativity. So although, in retrospect, it's a very important experiment, we don't think of it as being essential to Einstein. He was just that smart. He figured it out mainly from the math of Maxwell's equations. Yeah. There were others too, though, right? Einstein would be the first to give credit to people like Konrad Lorenz. Other names should come to mind, but they don't. All right, so I've just made an extraordinary claim. It requires extraordinary evidence, which I have not shown you. But I'll say this. This claim is the most carefully tested claim in all of physics. It's been tested for 120 years. Nobody's found any piece of evidence that denies it. Now, it could be wrong tomorrow. Again, if you can do that experiment, if it can be replicated, you got yourself a good prize. What further weirdness does C's invariance imply? All right, let's see. Here it is. C is 3 times 10 to the 8th, 300 million meters per second. And it's a special number. And it's not just a speed. And that's weird. It sure seems like just a speed, albeit a very weird speed. C squared, C times itself, too, has special meaning and weird units. Let's look at that. All right, here's C squared. Remember, we're working from right to left in our equation, E equals mc squared. So here's the value of C squared. 3 times 10 to the 8th times 3 times 10 to the 8th in meters per second. And here, if you're a bit rusty in your high school physics, you got to remember that you treat the units, meters and seconds, as if they were numbers. So when we multiply the numbers together, that's pretty easy. 3 times 10 to the 8th becomes 9 times 10 to the 16th. And the units multiply each other. So we get meters times meters over seconds times seconds. And so we're gonna abbreviate that, we're gonna approximate it, hence the wavy line, to be 10 to the 17th meters per second, meters squared per second squared. Now, admittedly, those units are weird. I know what a square meter is, right? Maybe I've got a meter here and I've got a meter here. I might buy a square meter, if not a square yard of fabric someday to make a better looking jacket. But a square second, what is a square second? No one knows what a square second is. Even Einstein didn't know. It's a mathematical shorthand. All right, so, but it's there. The units of C squared really are 10 to the 17th meters squared per second squared. A very big number. Okay, so we have conquered the right-hand edge of this equation. Let's see if we can understand mass a little better. What is mass? Okay, the symbol will be little m. And I want to remind you that early on we defined the two quantities that constitute speed, distance, and time as fundamental physical dimensions. The dimension of space, dimension of distance, and the dimension of time. Hence the capital letters there. Well, nobody's been able to figure out how to take mass and dissect it into some combination of length, distance and time. So we have come to understand that there's a third basic physical dimension called mass. Where did it come from? Nobody knows. It's a fundamental constituent of the universe. Okay, fundamental property, let's put it that way. But we can still ask, in what units should we measure it? By the way, it's not the quantity of matter. It is something special, but it's not just how much stuff there is. It's not weight. And I know you've heard about this, that when you go to the moon, your mass is the same as it is on Earth, alas, but your weight will be about 1/6 of what it is here, because gravity is weaker on the moon. Weight measures gravity's effect on mass, but it's the mass that's essential. The only way to change your mass is lop off an arm or lose the hardest part, lose that mass. I have a mass loss program you want to subscribe to. Give it a check. All right, so it's not quantity of matter, it's not weight. What other equation involves mass? If we're going to try to figure out what mass means, can you think of any other equation, perhaps from physics, where you've ever seen a little m or the word mass? There's an m in momentum, but that's not actually an equation. Yes,
F
Charlie.
equals MA.
F equals ma. Yeah. F equals ma. That's Newton's second law of motion. It's got the name Newton attached to it. It's pretty darn important. F equals ma. Force equals mass times acceleration. There's that little m. And so a little bit of math, dividing both sides of the equation by a, trying to isolate m, I get m equals force divided by acceleration. Does that really help? Yeah, if we think about how to make that, if we think about what those words mean. I've got a hunk of metal here, shiny cylinder, and if I apply a force to it, a steady force, especially if I'm out of deep space and don't have to use my other hand to hold the cylinder, the mass will accelerate. Forces cause accelerations. Yeah. And the more force, I say for a given force, if the acceleration here, look at the denominator, if the acceleration is big for a given force, that is, if the denominator here is big, then the fraction is small, and I have a small mass. An average force giving a lot of acceleration means a small mass. And I guess oppositely, for a given force, if I have very little acceleration, I try to push on this thing, and yet it's very massive, that small acceleration arrived at by applying a typical force gives me a big mass. This equation does tell us conceptually what what mass really means. So let's look at the units that we've agreed here. Mass is resistance to changes in motion. We'll get to units in just a second. Mass is resistance to changes in motion. That's where that acceleration comes in here. If this hunk of mass were just cruising through space out there, let's say between Earth and the moon, it would just coast along, moving through space. Yeah, but not like moving through water, right? I don't know what it means really to say moving through space. But if I apply a force to it, it'll change its speed. Forces cause accelerations. And that gives us a way to, a question?
I was just wondering if that was the way that the force against an asteroid keeps it going at a certain speed.
Okay, now you said a force against an asteroid keeps it going. Well, but there are no such rockets acting on asteroids, right? Let's say most asteroids are out there between Mars and Jupiter asteroid belt. They're cruising around the sun with no rockets attached. There is a force on them, but it's a central force. It's the force of gravity of the sun that keeps them from flying off in a straight line. Yeah, but there's no force pushing the asteroids around. And indeed, they're not changing their speed. They're changing their velocity, their direction. Yeah. But let's go back to this for a second. Changes in motion. If you want to get an intuitive feel for how to measure something's mass, change its motion. Use the wiggle test. If something is more massive than this is a 1 kilogram mass, I'll be able to feel it when I wiggle this. Not when I hold it in my hand. I'm measuring its weight now. That's not what I'm interested in. Weight is proportional to mass, but I want to know, here's this mass, so I wiggle it. A paint shaker is a good device for measuring something's mass. Use the wiggle test to measure something's mass. And I'm going to encourage you here, measure mass with the wiggle test and get used to this idea of a kilogram, right? So if you like, just to get a feel for it, as this goes around, sure it's shiny and pretty, but that's not the point. Wiggle it. When you get this thing in your hand, shake the kilogram to feel its inertia as measured in kilograms. This is a 1 kilogram's worth of inertia. And I shake. Yes, sir?
This is, torque.
Uh-oh.
So a torque wrench often measures in newtons per meter. Is there a relationship there? I mean, you're trying to force it. I'm just trying to understand.
Yeah. Torque is force times lever arm. So it's usually in this case, it might be in pounds, pound-feet, or foot-pounds. Yeah, there's no per in there, they multiply each other. But that's really a different subject.
There's no
Although,
relation to mass.
well, how about this? You can't apply a torque to nothing. So how the thing you're torquing responds, how it undergoes angular acceleration, turning acceleration, that would depend on its rotational inertia, its rotational mass. So while this thing has 1 kilogram, where'd it go? Missing some. Oh, yeah. So this thing has 1 kilogram of inertia, of mass, that's not the same, quite the same as its rotational inertia when torque becomes important. Yeah. Yes?
Yeah, so when you say kilograms, I immediately thought, could grams be actually be a better measurement for mass? Because kilograms it's like 1 kilogram is 1 kilogram. How about like a lighter things like 5 grams, 10 grams, 20
Sure.
grams?
Yeah, the international folks, the international system has just agreed to use the kilogram, 1,000 grams, as the standard. But it could be a decigram, I suppose is that 1/10 or 10? Anyway, it could be a gram itself. We just agreed, it's too bad that a fundamental unit in the SI system has that prefix kilo in front of it. That seems odd, but it is there.
It's not, because it's like, if it's only kilogram, it's like 1 kilogram equals 1,000 grams. So why not, use grams, as a simpler,
Yeah.
form of measurement rather than, kilograms, which is like, you need like a kilogram of something
Yeah.
to establish mass.
That's a good question. I don't have a good answer. But how about this? I'm grateful that the kilogram is a unit, because just like the unit of distance, the meter, and the unit of time, the second, the kilogram is a fairly handy physical human scale unit. If our unit was 1 gram, it's too small to be very practical to use. So we settled on a kilogram. But it's based on the gram, at least grammatically. Yeah, but 1 second, 1 heartbeat, 1 meter, about a yard, 1 kilogram. On Earth it weighs 2.2 pounds. That's a good unit that we can get used to with a little practice. All right, so we're 2/3 of the way there. Not bad. But now we got the tough one. E equals mc squared. Let's talk about energy. What is this capital E? Okay. Maybe you've heard that energy is proportional to ability to do work. That if you have a lot of energy, you have a great ability to do work. That's not a bad definition, but you can guess we're going to have to be more precise if we want to understand this equation. All right, so how about this? Consider it that whatever energy is, it's special. Right? Somebody mentioned momentum earlier. That's a nice physical quantity. But in the US government, there's no department of momentum. There's no department of mass or department of speed. Energy is really important. Personally, I find it important. I like more energy rather than less. And it's deeply built into the universe, but in a complex way. So E is special. Here's some different types of energy. If we're going to understand the capital E, let's consider the different types. First, you've heard of kinetic energy, right? The energy of motion. And I'll give you some examples of this in a moment. The energy of motion. Thermal energy, also known as heat. This is a kind of kinetic energy, but on a microscopic scale. The kinetic energies of the molecules of which something is made. And we have potential energy, the energy that is not expressed as either heat or whole-scale motion, kinetic energy. All right, kinetic, thermal, and potential. And I better clarify that. But notice that there are other kinds of energy here. Light energy, electromagnetic radiation, light, right? Sound energy, chemical energy, nuclear, and the list goes on. We don't really know if we've discovered all the types of energy that exist in the universe, but we got a pretty good list already. All right, here's the unit, the SI unit of energy. Right? Energy is not a fundamental physical dimension. dimensionally speaking, right? Mass, length, time, not energy. Energy is built up from them somehow. But we can at least talk about the unit. The unit of energy is the joule, and it's about the energy of one handshake. Now, you may have heard of the unit, the watt. Now, that's not a unit of energy. That's a unit of energy use. How much energy do you use per second? That's measured in watts. So when you shake your hand, your power, that's the term there, watts measures power. Your power is about 1 watt. A handshake is a 1 watt powerful action. But one handshake itself takes about 1 joule of energy. Again, I'm glad this is a fairly physical unit that I can get a grip on. Pardon me. All right. What other energy units have you heard of? Please, offer some. You know you pay your bills, PG&E. How about some other units you've heard of for energy? A little louder, please.
BTUs.
BTUs, wow, yes, British thermal units. Those are units of thermal energy, BTUs. Horsepower, okay, but as that name implies, it's a power. So if I say 1 horsepower is something like 750 watts. So again, not quite an energy, it's energy per second. Okay, so not horsepower. Ergs, yes, an erg. An erg is a fraction of a joule. I can't remember what it is. It's a tiny amount of energy. How about when you... Ooh, kilocalories, excellent. Or capital C if we're dieters. You cut down on your energy intake in your food, and you're trying to reduce those capital C's, those kilocalories, or calories with a capital C. That's energy also. That's chemical potential energy. I gripe when I have to pay my PG&E electricity bill. Yeah. What are the units there? Very strange. Kilowatt hours, right? Kilowatts a unit of power, and you multiply by time, 1 hour, and you get a huge amount of energy. Right now, PG&E is charging something like, it varies depending on time of day, but or your particular plan, but something around 30 or 40 cents per kilowatt hour. And a kilowatt hour is a huge number of joules. In fact, let's take a look at this. So 1 joule of energy is roughly the energy of a handshake. 1 calorie, that's capital C, that's a food calorie, is 4,000 joules. There's a lot of energy, a lot of handshakes in an apple or a Hershey bar. A calorie, 4,200 joules. A kilowatt hour, there's that PG&E bill, is 3.6 million joules. And as much as I whine about that 30 or 40 cents, that's a lot of handshakes for 30 or 40 cents. It's really a good deal. And there's a frightening number, 1 megaton. Megaton of TNT, that's an explosive energy that ultimately gets turned into heat. And that's 4.2 times 10 to the 15th. I don't know the number. I don't know how to say that number, but it's frighteningly big. All right, so we're getting a handle on energy, at least its units. That's good. All right, but I promised a deeper look into the meaning of the different types of energy. All right, first, let's be practical here. Energy as good. Whether you're trapping it as solar energy to make electricity, or you're building a barn, perhaps, as a barn raising adventure of your neighbors, or you're a dancer. That kind of energy here's our expressions of it that we'd say we put a moral quality to it. Good. All right, how about energy as harm? The energy of a car crash, of a thermonuclear detonation, or even of a knife in the back. Notice that it's interesting that energy can really do harm. In the end, regarding projectiles or things put into the body on a large scale, I don't mean viruses now, but on a large scale, the more energy the object has, the more damage it does. So bullets are more damaging than blades because bullets have more energy. Now you could be perhaps skilled with a blade and really do somebody in well, cut a vital source of blood or blood conduit. But on average, bullets, because they're more energetic, do more damage, more harm than blades. Okay, lots of types of energy. Here goes that list. All right? How about kinetic energy? Energy of a sprinter, of a bullet, the energy of somebody jumping off a cliff. As they fall, they gain kinetic energy and they lose potential energy. The woman on the high wire there, she's got the energy that gravity gives her as she's above the crowd, the admiring crowd below. This little kid's got elastic potential energy in his swing shot. And both the apple and the battery have stored chemical potential energy. So we saw kinetic energy, energy of motion just a minute ago, potential energy, and now we go to thermal. That is the random vibrational kinetic energy of molecules. And here we see it in the car crash, the blade and the bullet and the bomb. All right, those are the big three of energy. There are other types, but that's good. Thermal energy, by the way, is the most sorrowful of the types of energy. It's the graveyard of all energy. Because as far as we know, all the jewels in the universe will ultimately end up as pathetic random vibrations of fundamental particles. But we don't know. That's what's all the time off. The rules could be changing. This physics business, who knows if that's true? Really, we don't know if it'll be true forever, but it's been true for a long time. So thermal energy is the fate of these other forms of energy. All right, pretty good. We're done. No, we gotta get to the heart here. What is this equation saying? All right, let's do just a bit of algebra. You see the equation here. I'm going to divide both sides of the equation by c squared. Now, come on, you came to a talk on an equation. You've got to expect some math here. All right, so I divide both sides by c squared, both sides of this equation. There's e over c squared, and the c squareds cancel here. So I get e over c squared equals m. I'm going to just flip the equation around, m equals e over c squared. And now I'm going to isolate this factor right here. So it's m equals e, mass equals energy, times this funky number, 1 over c squared. Now c squared is a huge number, so 1 over c squared is a very small number. E equals mc squared can also be written m equals 1 over c squared, m equals e times 1 over c squared. And here's where I claim that giveaway idea at the very beginning, the takeaway idea, becomes evident. Energy has inertia. If I have energy here, as long as I multiply the energy in joules times this number, I will find out how much inertia that energy has. But come on, energy has inertia? Show it. I hope you say, Tucker, show us. All right, examples. All right, how about this? I've got here a portion of a slinky. All right, sorry. All right, and what I'm going to do is shake the slinky, and I'm going to use the wiggle test to try to see how much inertia this slinky has. Oh, thank you. All right, I shake it. All right, I got my wiggle test skills finally honed here. All right, now, well, in fact, I'm going to do it with 2 hands. All right, yeah. Now I stretch the spring. I haven't changed the spring in any way, I just stretched it. I've put more elastic potential energy into it, just as the kid did when he pulled the slingshot rubber band back. This spring has more potential energy than it did a moment ago. And so now I shake it. Ah, yeah. No. I wish, but no. Okay, maybe I'm just not sensitive enough. Let's try something else. Let's see. Let's try a dead battery versus a fresh battery. All right, now you have to trust me here. This battery has a D written on it. I wrote it. It's a dead battery, right? But this is a nice, fresh D cell, Duracell, D cell, fresh battery, extra chemical potential energy. Dead battery. I shake it. Wiggle test. Not much inertia. Oh yeah. That live battery? Yeah, just go home and see how dead your batteries are by shaking them. No. No, this is not working. All right, one more test. I have here a very special box. This is a magic box. It's made of wood and a little bit of metal. It's got a metal latch. But what makes it really special is what's inside. And what I'd like you to believe is that this pathetically wedged in bit of aluminum foil makes the inside of this box a perfect reflector. Imagine perfect mirrors inside this box. Okay, so I go into darkness, I close the box. I shake it. I want to feel the inertia. The wiggle test is saying, I got it. You know, it's about half a kilogram. It's not as massive as the shiny cylinder. Okay, about half a kilogram. And now I open the box. I take my green laser and I shine it in the box. And I very quickly close the box. So the laser beam is now bouncing around inside the box. This is a box made of wood and metal with air and light on the inside. And light is energy. So I shake the box. Oh yeah, now I can feel it. And it's got the extra inertia of that comes from the energy of the light in the box. Okay, well, everything I've just said was a lie. It's only a lie because I'm not sensitive enough. The wiggle test, as done by a human, is not good enough to detect the increase in inertia given by the light in the box, or the electric potential energy in the battery, or the stretchedness, the elastic potential energy of the spring. But they really are more massive because of those energies. All right, empty box versus light-filled box. How much inertia does 1 joule of energy have? Let's suppose that when I shine that light and that laser into the box, I added 1 joule of energy. Let's do the calculation. See if I can calculate how much extra inertia that box gained. What conversion factor takes us from joules of light energy to kilograms? Conversion factor, what is that? Here it is. Recall the conversion equations between distance in yards and length in feet. This is to remind you of what the heck a conversion is in physics. All right, so let's try. L is a length in feet, and D is a distance here in yards. So I wanted to convert, see down here I said try 100 yards. So I put in 100 right here. 100 times 100 yards. I gotta treat the units as if they were numbers. So D is not just 100, it's 100 yards. 100 times 3, that's easy, 300. A yard, the units here, yards, times 3 feet per yard, the yards cancel. And I'm left just with 3 feet. Of course you knew that. If I asked you how many feet is 100 yards, you'd say, duh, 300 feet. But the math just makes it harder, but it makes it also more universally applicable. This is an easy way to approach problems once you get used to it. Or if we try 100 yards, all right, if I say, I'll see if I can turn this around. Hang on a second. All right, here we go. Here we've got those same 2 equations, right? Length equals distance times 3 feet per yard. There are 3 feet in a yard. That's a conversion factor. I multiply that by any distance in yards, and I'll get numbers of feet. And this is a conversion factor, 1/3 yard per foot. Just listen to the words. How many yards are there in a foot? 1/3. 1/3 yard per foot is a conversion factor. So if I have 300 feet, and I multiply that by 1/3 yard per foot, I get a distance of 100 yards. All right, so compare these equations with equations for energy and mass. E equals m times c squared, this is up here, and m equals E times 1/c squared, right? This is our alternate way of writing Einstein's good old equation. All right, so these are our conversion factors, not for yards and feet, but for joules and kilograms. What's the inertia? What's the inertia of 1 joule? Use the equation. The conversion factor is 1 over c squared. So we stick in the numbers. M and E conversion, here it is. M equals E, the energy we want, whose inertia we want to know, times 1 over c squared. We're imagining we put 1 joule of light into the magic wooden box. All right. 10 to the minus 17th, second squared per meter squared. Yikes, that's such a dinky number. That's what 1 over c squared is. All right? So no change here except plugging in the well-known, in fact, universally accepted value of c squared. All right, and now I put in my 1 joule of light when I put in the laser light into the box. Now I have to evaluate this. What am I going to do with these funky units? Well, it turns out a joule, I warned you, it was not a fundamental dimension. It's itself constructed out of these things. A joule is a kilogram times a meter squared divided by a second squared. So since I treat the units just as if they're numbers, I multiply these units by these units. The numbers are easy by comparison. I get 10 to the minus 17th, that's the number, and the units do some miraculous canceling. 10 to the minus 17th kilograms. The mass that I added to that magic box, because of the light beam once introduced, is 10 to the minus 17 kilograms, right? There it is. Yeah. No wonder I can't feel it. It's too pathetic. Yeah? And that was true with the batteries, dead versus live. That was true with my little Slinky. The energies that I was adding or considering relative to each other were just too small for a human to notice. But before coming tonight, I did a little calculation on, a couple of years ago, I purchased an electric vehicle. And you know, electric vehicles have very good electric batteries. They store a lot of energy. And it turns out that every time I fully charge my car, I add to the mass of the car 2 or 3 micrograms. You know, big deal. Like, that doesn't cut down on the mileage I get. But it's still remarkable. Even that huge amount of energy that'll drive me maybe 300 miles if I'm lucky, even that amount of energy, it's something like 77 kilowatt hours. It's a lot of energy. Still, only 2 or 3 micrograms of inertia. But it's still, the point is, the equation does work. It's just hard to measure with macroscopic, with large objects. The Wiggle test fails to detect this puny mass. Right? So what do? Well, let's look at the reciprocal conversion. Instead of saying, how much inertia does 1 joule of energy have, let's say, how much energy does 1 kilogram of mass have? Or how many joules is 1 kilogram of mass? Start with E equals mc squared as usual, right? And E equals m times tau. Now it's c squared, right? Not 1 over c squared. 10 to the 17th meters squared per second squared. And the m we're going to say is 1 kilogram. I want to know, when we're converting kilograms to joules, how much energy is this? Well, I think you see what's coming. That's 10 to the 17th. Again, the numbers are easy. 1 times 10 to the 17th. And the units are kilograms times meters squared divided by second squared. That's a weird unit, but you have seen it before. That's a joule. 10 to the 17 joules. 1 kilogram of mass is, or at least has, 10 to the 17th joules of energy. That's a serious amount of energy. Yikes. Right? It was very brave of you to handle this kilogram. Because in a sense, this is 10 to the 17th joules of congealed energy. Yeah. You know, 1 handshake, let's say it's a slap, like a handshake. That could hurt. But imagine 10 to the 17th slaps all happening simultaneously. That would be rough. Here it is. 1 joule is 10 to the minus 17 kilograms. Beauty. Can't be measured by humans easily. But 1 kilogram is 10 to the 17th joules. Notice the equation. We're saying these are the same thing. How can a kilogram of mass be equated to something in energy units? Because energy has inertia. That's the punchline of Einstein's equation. Mass and energy are two names for the same thing. He's laughing at us. He's laughing with us because this is so cool. All right, let's see. Here's a summary of key insights tonight. Energy has inertia, has mass, as detected by the Wiggle test. And m equals E times 10 to the minus 17th. But that's not much, right? Because 1 over c squared is this puny number. Mass has energy. E equals m times c squared, 10 to the 17th, and that's a lot. So c and c squared are special numbers. C isn't anymore just the speed of light. It's now a number that's involved in a conversion, a mathematical conversion factor relating energy and mass. Here's one more takeaway tonight. Nuclear events involve 1 million times more energy than chemical events. So you remember I mentioned Enrico Fermi and talking about the Wonderfest event in 2 weeks, the Fermi paradox. Well, Fermi was, as far as I know, the first human with his team to effectively harness nuclear fission to produce a little bit of excess energy. And that is a nuclear process. So when, say, a uranium atom splits in two, not a very big bang, it's just one atom, but there's 1 million times more energy there than when a TNT molecule breaks apart. Nuclear events, as were developed by Fermi and others, are 1 million times per event more energetic than chemical events. This is good news for nuclear power and bad news for nuclear war. If you've liked these ideas tonight and you'd like to revisit them, there is a video on YouTube that you can find by searching for radical physics. Radical in the sense of at the root. That's what the word radical means. It doesn't mean wild. It just means fundamental physics. And the talk here is entitled E equals mc squared and the equivalence of energy and mass. It's the 14th episode in a series called Radical Physics. Okay, I promised to come back to this. I think I promised at the end of the talk. And how are we doing here? Not bad. How about this idea of Einstein saying, if only I had known, I should have become a watchmaker? Yeah. How about if you offer something? What do you think he meant about this? What he meant by this?
Doesn't this idea have something to do with time, though? So how does time fit into all of that?
He just didn't want the bomb to get heavy.
Yeah, I'm assuming this is a reference to the bomb, but not necessarily to, let's say, the understanding of E equals mc squared. Just the practical unleashing of the energy that's latent in all mass that can be extracted with difficulty from certain atoms. Again, I'm worried that he meant, if I'd known this, I wouldn't have even become a scientist.
I
Yes.
think he was referring maybe back to the way his E equals mc squared was used to create destruction.
Yeah.
Nuclear energy in a bomb
Yeah.
that killed masses of people. And he regretted that he'd ever discovered the root of mc squared.
Yeah. Maybe some of us saw the movie Oppenheimer last summer, and Einstein is featured in that movie. But you notice he wasn't there at Los Alamos, and he wasn't even with Fermi in Chicago, splitting the atom. He was I think in New Jersey, in Princeton, just doing his theoretical physics. But even from there, he said, I think he was saying, I know that my work, principally in quantum mechanics, not in this field, was radical physics. It was at the root of physics, and it's that physics that was helping to bring about the horrendous energy of these weapons. Yes.
Let's have a
Yeah. It's, all right, yeah, so what, how about, remember I said that nuclear events are per event 1 million times more energetic than chemical. All right, so I don't know what this is made of. Say it's chrome-covered iron. Chrome and iron are elements of the periodic table. You know, I could maybe do some chemistry with them, but to affect their nuclei, if I could take apart the nucleus of each atom in here, then I would somehow be getting at the energy that's in this, the 10 to the 17 joules. When Fermi split the atom in Chicago, he was dealing with uranium, right, which is denser than this. Maybe there were cylinders of uranium, but the special property was those atoms, Fermi could figure out how to break apart to release that pent-up energy in the nucleus. But luckily, I guess, on the other hand, maybe it's too bad. Chrome and iron, you just can't do that, especially iron. Iron is the dead end of nuclear activity.
You call it chemical energy or something?
No, so nuclear potential energy, that's mainly what's here, yes, yeah. I guess I just could have said those words first, I'm sorry. Yeah, nuclear potential energy, yeah, thank you for the question. If you've, we'll take some questions now, but I want to end with that reason we're here, right? Maybe not why we exist on Earth, but how about this? We've just climbed a mountain, we understand something pretty deeply, and I hope it's been fun. Thank you for listening. Okay, any more? Oh, sir, yes, please.
So at the start you asked what speed we're traveling. And if we're mass and therefore energy, can that be measured in frequency and that related to speed?
Wow, okay. Okay, now here's something that I know if I'm not going to directly answer your question. This is the trick of the good speakers. You hear the question, repeat the question, but change it just enough that you can answer it. How about this? Right now, relative to the floor, I have no speed. So my kinetic energy is 1/2 mv squared, 1/2 my mass, times my speed squared, but my speed is 0, so I've got no kinetic energy. If I take off, if I run at 10 meters per second, I don't think I can do that, then I'd have some serious kinetic energy. What's the difference? My running. But why, when I'm standing, relative to you, I have a certain number of joules of kinetic energy. But if you were to run along with me, you'd say my speed relative to you is 0. So I've got no kinetic energy relative to you. So in this way, kinetic energy is a relative quantity like speed. Did I weasel out of the question sufficiently, or did I?
Yes.
Was it, okay. Yes.
So C is the speed of light. What is C squared?
Yeah.
I mean, where did that come from versus? I
Yeah.
mean, now it's proven that inversely C squared works.
Yeah. You'll notice
Why
that
not
I.
cube?
Sorry.
Why not cube?
Yeah. Why is it? There's that cartoon you saw at the beginning, right, with the poor Einstein with his head on the board saying, "What is the answer?" And he just hasn't written. He's got E equals mc cubed, E equals mc to the 7th. And the Kingsley said, "Okay, everything's all squared away here. We got everything squared away." Yeah. So why is it c squared? Notice how I very carefully did not derive the formula. Yes, and so nothing up the sleeve. I could tell you, there is a book, there are probably several books, but I have actually owned such a book, and I've read it. It is about the derivation of E equals mc squared, and you can kind of get it. Let me go back. Notice the paper here in the background. Does the inertia of a body, a mass, a thing, depend upon its energy content? And you can bet you don't start a question like that on a paper unless the answer is yes. Because who would think that the energy will affect the inertia? But in this paper, there's a derivation, and there's nothing, I don't even think there's any calculus. It's just a lot of careful thinking and using this remarkable insight into the speed of light, that the speed of light's invariant. But that's the best I can do, sorry. You get a full refund for your admission charge, if you're not happy with it. Any other questions? Yes, sir.
No, I'm
Ma'am,
just
sorry.
gonna comment.
we're showing the background microwave radiation as far out as we can see.
Oh.
Looks just like this.
All right, I'm sticking with that explanation. All right. It's the microwave background. All right, thank you. Yes.
Just not a question. I would love to see the picture, the cover of the magazine again.
Oh, the cover of the
Then you would have to
magazine.
go
Oh, yeah,
forward
yeah. Here we
on
go. There we go.
There we go.
Yeah. I can almost make out the date.
That's what I'm looking for.
45.
It is 45. Shoot. Oh, it's up there. July something, 1945. Could that be?
Yeah.
Trying to think of that. Oh, yeah, yeah. Okay, yes.
Yeah, then if that magazine was from July 1945, that would have been like a few weeks before Hiroshima and Nagasaki happened.
Yeah.
Which would have been like, foretelling the future.
Right.
Yeah.
Possibilities.
Hmm.
Yeah, because it's like, you know what happened like earlier this month. It's like, yet another anniversary of the nuclear bombing of Hiroshima and Nagasaki.
Yes.
And then with that prelude from July 1945, oof, that was like, foretelling the future.
Yeah. Huh. I'm pretty sure that says July. Maybe it's,
Maybe it was responding to a nuclear test.
or maybe they antedated their magazines back then. Now they give you a month. They give it to you a month ahead. Yeah. Sorry, I don't have an answer for that. That is a genuine cover of Time magazine. It's, unless somebody really fudged the graphic, and I didn't do that. All right, you were a great audience. Thank you for putting up with the jacket. All right. Good night, all.
Oh, 1946.
46?
July
July?
1st, 1946.
46. Wow. So it took a while for
Was
this.
discovered.
Yeah. Thank you.